Speaking of reliability, a podcast with good friends talking with you about reliability engineering topics. Welcome to Speaking of Reliability. This is Fred Schenkelberg.
And this is Mojan Sohi. Hi, Fred.
Hey, Mojan. Good talking to you again. So what's on your mind today?
Well, I've been thinking a lot about damage modeling, Fred, and how much it is used in reliability.
Why am I not surprised? We just spent half an hour talking about
it. Yes, it's been a topic.
It's time to hit record. Yes. That's what the phrase was.
Yes.
Got away from us a little bit.
Yeah.
But so when you're talking about damage modeling, it's like I'm thinking of, I got a call from a company that made brakes for airplanes.
Mm-hmm.
And I said, oh, that's interesting. Are they like car brakes? It goes, oh, no. They're on the big Boeing and Airbus machine, aircraft, big aircraft. And I said, oh, okay. And when are they used? He says, well, they're partly used when they're landing, which is the most important part, we think, but they also need to work when they drive up to a gate, they docking into the gate, basically. And as he's saying this, I asked him, and I'm at an airport, and I'm talking to him, and I asked him, so you don't know how long your brakes last? And he goes, no, nobody's ever asked this before.
Oh my God.
And I'm watching this Airbus 320 coming up to the gate, and I moved out of the way. I was like, I'm not going to stand right in front of this thing.
That's surprising. They really didn't know. I know someone who's worked on more on like the catching mechanism on aircraft carriers.
Mm-hmm.
Like the person I know has done like damage modeling for those to make sure that they last as long as they're supposed to under those loads.
Because if it snaps at the wrong time, this multi-million-dollar jet goes off into the deep end.
Exactly.
Yeah, no, it's the modeling part. The other, have you read the book about the design of the 777, the Boeing 777?
Oh, I haven't, but I've heard of it actually. Yeah, it's got list.
And I think there's a documentary about it. And my favorite part is they were the newest, biggest, coolest thing they were doing was these composite wings, and it really reduced a lot of weight. And they only test one wing.
Mm-hmm.
And talk about damage modeling. They had all kinds of cool things about what they thought would happen. And they ran this test, and the wing went, 20% further than they thought it would. And they said, oh, damn it, now it's overweight. And they didn't have time to redesign
it. Yeah. Yes. So maybe would it be good to start with just talking about what damage means in the context of reliability? I'm not sure.
Oh, sure. Yeah, that's a good idea.
How much of our audience would be familiar with it? Because I've heard, I think I'm learning that there are people that have not used it before. So maybe it's a good place to start.
Okay. I think of it as there are so many different failure mechanisms that, for example, corrosion on steel.
Mm-hmm.
There's just less steel there now. And it's not like copper where you get a little bit nice green Pantene to it and it stops. It's steel. Some types of corrosion will go right through it, and eventually you won't have a beam anymore. You won't have a truss anymore. You won't have a rebar anymore. And that rate of damage is a chemical process. You can predict it. You can model it. You can create an equation that says under these circumstances, this is how long it's going to last. And then you can decide, do you add barriers to that, or, well, heaven forbid, paint it or something like that. There's all kinds of ways to mitigate it. But brake pads, every time you hit the brakes, my ex-wife in particular, she would just anyway.
Yes.
She went through brake pads, and nowadays, cars are so instrumented up, they can probably tell you before you need to know that your brakes are about to be failing, and you can go deal with it. But the damage models work on things, in my experience, on things that wear, corrode, diffuse, something that either removes material, adds material where you don't want it, or changes the physical properties of the materials involved.
That's right.
Is that fair?
Yeah, I think that's very fair, and I probably the most well-known association with this or type of this is probably Miner's rule, which maybe our listeners have heard of, which is essentially describes like the states at which like a cycle consumes a fraction, like every cycle consumes a fraction of a component's life.
And the more load that cycle has, it's proportional to how much damage. I use that for crack propagation.
Yeah,
you know, the more you pull the end of the crack apart, the further the crack's going to proceed. You know, and if I do lots and lots of little ones, they count too. Now there is some nuances in all this stuff, because even like in crack propagation, there's a part where it's I want to say it's like a rubber band. It's elastic, right? It can withstand that stress without the crack propagating. And then it crosses that threshold where it's not elastic, and then it has to stress relieve, and the crack propagates.
Right.
Right. And different mechanisms all behave slightly differently, but Miner's rule has a great application for, you know, if I'm doing thermal cycling and it's just nominal daytime temperatures, it's 20 to 40 degrees C, min to max, it's usually about 20 C per day in all the places I ever studied. And the daily average cycle. Now the highs and lows will be different, but the difference between high and low at 80th percentile is about 20 C. And well, I can go up and down 20 C in a chamber, but it's really hard to control a chamber to just do 20 degrees. You know, and stop and then come back and come, you know, like, whereas if I could go 100 degrees, I do a whole lot more damage unless I cross a phase transition in anything involved. And I can do much fewer samples. And it's an application of Miner's rule, where you can say, all right, well,
yes,
exactly. I'm overstressing it from what it should see, but the damage is proportional without crossing any barriers, then it applies.
Yes. And the goal is basically to try and find the bubble or triangle, if you will, depending on how you're plotting this, as to which the blob of area that you're essentially you are fine, and then outside of that, you know, you may have a failure. So the question becomes, how many of the accumulation of such cycles equates to, for example, one life, and then that's the window that you. Maybe that's the window that you design for. Maybe you design for 3 lives, depending on how much margin you want to have. And so you want to know when is it that you've reached past that point, and therefore may see failures. And back to your example about airplane brakes, that's you want to know where that window is, and then determine based on that, you can determine all kinds of things, such as your preventive maintenance windows, and you know, the just design changes that you may want to make, etc.
Yeah. Well, back to the brake guys, I asked them, you don't know? And they said, no, nobody's ever asked us. They do a complete replacement of the entire brake system. I think it was every 5 years. And
they were just doing a standard, like just like a
fixed number of flights,
fixed maintenance.
Yeah, it was fixed number of flights, and they've been doing that for decades and decades. And it's not just brake systems; there's all kinds of systems. And I think it's every 10 years that goes down to bare metal, the whole aircraft, and it gets rebuilt. The airframe's the only thing that really has to last a long time. But you can imagine nav systems and stuff like that. Those are leaps and bounds more technologically advanced than they used to be. So those kinds of things get replaced routinely. But the brakes, I didn't know that. And I said, this is not like a car brake pad, is it? No. There's all these other components and pieces and pistons and controllers and electronics and pneumatics and all kinds of weird systems that are involved in it. I says, that's got to be expensive. And that's why the companies are now asking us, well, could these last twice as long and still have plenty of margin? And they said, nobody ever asked us before.
Can we optimize the PM interval, such that it's not, you know, we're not just replacing replacing brakes that still have a lot of life left, and
they're taking these things apart and looking at the brake system and the mechanical parts, going, there's nothing wrong with this, and they're like, why are we replacing it? It's, oh, that's the regulations, that's what it was designed for, blah blah blah, and costing them $100,000 a shot. And it was a reasonable question. And then I told him that I slowly moved away from this nose of the Airbus 320 coming at the gate as we were talking, and he laughed. Oh, they're fine, And then 2 weeks later, I hear in the news, somebody's brakes. Either the pilot didn't hit the brakes, hit the wrong button, or whatever, and it hit the concourse.
Oh no!
Yeah.
Oh wow!
Nobody got hurt or anything. It touched the glass, and I was like, okay, well, there's a delayed flight in the works.
I wonder what sorts of, one of the things about understanding the degradation through damage modeling is that you are monitoring this degradation basically as you're going through, the tests that you've designed based on this. So you need to have some sort of metric.
And that's that aircraft wing part, right? Their modeling said it should bend to this point, and then we should see these stresses here, here, and here, which is beyond our limit. And it took them 20% more flex than they expected before they started to see the signals that it was failing. They didn't break it. They didn't break it right off or anything like that. But you're exactly right. Is the model gives you a real good picture of what you need to look for. So you know that if it's doing what it's supposed to be doing or not. It's
a very useful tool for that,
it is.
For that purpose. Yeah.
The old style engineering is you made the same thing 300 times. And like an engineering team would design and update and variations of, say, the same product over and over again for 20 years. And they would have a lot of field data. They'd have a lot of experience with their internal testing, but they didn't have a model. They had the engineer that said, oh, that should be fine, because they just knew from so much experience. Whereas when we start getting into more exotic materials, we started getting into more, when this fails, it's catastrophic, say an aircraft brake. I don't know why they didn't know how long it would last, but, and then you go to modeling. It's way less expensive than waiting 20 years to see if you're right.
Yes, and it allows you. The other thing that I was going to add is that as you're doing this and you're learning how fast things are degrading, it also allows you to set up detections and triggers and thresholds for, signals that may throughout service life indicate to you where you are in that life, which would prevent you from having a failure. So it makes me think of like, they must have detections for brakes not functioning. They must. I'm going to just pretend that they do, because otherwise
there's a lot of buttons in the cockpit. Who knows what they all do?
There's got to be some signal and some threshold that's been set of like, if it goes below this, or above that, whatever, there could be.
If there's no hydraulic pressure, then that's a problem.
That could be one. Yeah, exactly. Yeah. But you should be able to, through damage modeling, learn what these thresholds need to be, so that as your product is operating in its service life, you could be monitoring these through various sensors, and then know based on that read, generally where you are in life as well, and of course, then be able to plan your PM intervals based on that.
So 2 other thoughts here. One is that the design team also needs the modeling, or even the concept of the modeling, maybe not totally fleshed out, to say, all right, we have 100 different ways this thing can fail. Right? Which ones are relevant? And so the first pass is the engineering's judgment. It's FMEAs and risk analysis. And if this failed, would it be catastrophic? Yes. All right. We need to understand it. If this failed and nobody noticed, all right, let's move on to something else. Do our best, reasonable judgment, and go on. But the design team has thousands of decisions to make, and they're not going to create a detailed damage model for everything. Right? It's just, you don't have the time, energy, or resources to do it. So you narrow it down to, and the damage modeling can take 10 suspected major issues and probably narrow it down to 2 or 3 that you really need to focus on, and either engineer more robustly or monitor or do some other stuff. Because adding and tracking measurement systems on on a system is yet another way it could fail. Is more complexity, it's more power drain, it's more computer load. You don't do it lightly.
Yes.
It's only in the areas where it really makes economical sense. So I think that's the two, is when it gets feedback to the designers of, yeah, we really are good here, or here's our options, or do we do monitoring? And then the second one is monitoring is, in my opinion, a last resort. Is if you
yes,
can't
I agree.
design it,
yes, it should be as a last resort. I agree. Yeah. Yes, it's like but it's good to,
it's cheap insurance.
It's like a nice to have, and you, well, it also, I think, allows for, like, if you when you start out, you have some assumption as to what the distribution of your field stress is going to be, and your user base, you may have some assumptions as to what your 95th percentile usage looks like, but monitoring allows you to sanity check that as well, right? Like you can then look at, be like, oh, we thought that this kind of usage was going to be 95th percentile, but it looks like maybe it's actually, less than that or something. Or, our assumption is maybe it's narrower, maybe it's more,
I'm thinking of one more airplane story. Is I was flying back from Korea, and I don't know, I think it was the 777, and we were circling forever to get to San Francisco, and they finally said, "Hey, we're out of gas. San Francisco's not going to let us land in time, so we're going to land in Oakland." And the pilot came on and says, "We're just landing for refueling, and then we're going to take off and land in San Francisco." So the assumption that every flight only had 2 landings, or one landing, every takeoff had 1 landing per flight is usually the metric. Is we added another cycle of landing and takeoff in the middle of the flight. And I asked the steward, is like, so do we get an extra 500 points because it's an extra leg to the journey? And he's like, I doubt it.
It would only be fair.
You would think so, but
it would take like 15 minutes to get from Oakland to SFO. It's that's funny.
It took us that long to get out, taxied onto the runway, and
then you get up and then you come down immediately.
Yeah, we flew to San Jose, circled, turned around, and came right back on the flight path. It was, I think we maybe got to 4,000 feet. It was cool. And I'm coming through customs, or not customs. Yeah, customs, and or whatever it is, the border stuff. And his pilot's in front of me, and he's talking to his buddy. He goes, "Did you hear about that plane that did a hop to, landed in Oakland to refuel so they could land in San Francisco?" And I looked at him and said, "I was on that flight." So they said that pilot's in big trouble. Just socially, I bet you they were going to just harass him.
Oh, yeah, they were not going to let that go for a while.
No, they're not going to let that go. But anyway, modeling, damage modeling is a specific subset of modeling in general, but it uses the same principles. You gather information, you look for patterns. Some models are well known and existing, like Miner's rule, Black's equation, I'm drawing a blank. The one for the solder joints, Coughlin-Manson is another whole series of them. There's a lot of models because they are useful. They're not perfect by any means, but it sure helps you make better decisions. And I think that's why I'm surprised we hadn't talked about damage models before. It's only 1,000 some number of topics.
And there's much more that we can that we could get into it with. Like, I think the benefit, another benefit of it, for example, is that you have, it's like a normalized form of stress, if you will. It's a good way to describe this. So if you have different ways of using a product, damage modeling allows you to kind of just not normalize the stresses from those different ways and be able to envelope them into one profile, which you can use in testing. And as you mentioned, like, it's basically, with the amplitude, like you can increase the amplitude and then accumulate damage faster, which is also a benefit for testing. And yeah, just lots of things that you can do with damage modeling. It's a very, very good tool, very versatile tool.
Yep. Yeah, no, good. It's a good topic. And yeah, you're right. There's a whole pile of other things we can talk about it with it. But, if you've been listening to this and going, well, that sounds like accelerated testing, or that sounds like this or that thing. It's one of the funny things about reliability engineering. Every consultant has a different name for it, whatever it is. So you might be calling it something different, or you might want to learn some more about it, which I do too. I'm always learning more about this kind of modeling approach and where it's useful, which is a lot of places. So, how are you using this kind of approach, and how has it benefited for you? Or if you have questions on how to get started, that could be a really good basis for a future episode. So let us know. Head over to accendoreliability.com/go/SOR. And there's a couple of ways to get in touch with us there. Mojan and I and the other hosts are available through LinkedIn and our About pages. And we'd love to hear how or love to hear from you. That's the easiest one for it. So please join the conversation. We look forward to it. So thanks so much, Mojan, for bringing that one up. And we should have hit record 10 minutes earlier, but
I think we got most of what we talked about. So yeah, thank you so much. Thanks for indulging.
All right, cool. Thanks so much. We'll talk to you soon.
Talk to you soon.
Thanks for listening to Speaking of Reliability. We invite you to join the conversation. If you have a question or a topic that you think we should discuss in a future show, please let us know. You can find a comment box below the episode show notes, or just leave a note as part of a review on iTunes.